Mentor Handbook for Training, DNN for Semiconductor PPC Math Formulas per Node and DNN Processing for Output. https://udo.be/o0wkncicxmg. Mentor Handbook designed specifically for training a small group audience, video titled DNN for Semiconductor PPC, Math Formulas per Node and DNN Processing for Output. Author, Pradeep K. Suri. Mentor Handbook for Small Group Training. 1. Welcome and Introduction. Welcome to the training session on Deep Neural Network, DNN, for Semiconductor Production Planning and Control, PPC. This handbook is your guide to effectively deliver insights, facilitate discussions, and support learning for a small, focused audience. The session is grounded in a video that visually demonstrates how each node in a DNN is driven by specific mathematical operations critical to decision-making in semiconductor manufacturing. 2. Training objectives. At the end of the session, participants will be able to understand DNN architecture and node-level processing, correlate math formulas with AI logic used in PPC, interpret DNN outputs in the context of semiconductor workflow optimization, engage in interactive discussion on how AI is transforming production efficiency. 3. Audience. Since this is a small group session, begin by knowing each participant's background. Identify roles: engineers, planners, data analysts, and align technical depth accordingly. Acknowledge differing levels of AI literacy and make use of peer-to-peer learning dynamics. 4. Session structure. Structure your session in 4 parts. 1. Introduction to DNN and its relevance in PPC. 2. Video walkthrough with pause discuss play segments. 3. Whiteboard discussion on math formulas shown per node. 4. Interactive activity, interpret a PPC case using DNN output. 5. Layered walkthrough. Break down the DNN into layers. Input layer, feed variables like wafer quality, machine load, temperature, and design complexity. Hidden layers, feature transformations using sigma, sigmoid, ReLU, rectified linear unit, 10, softmax. Output layer, generates forecasts for resource allocation, yield estimation, and bottleneck resolution. 6. Mathematical integration. At each node, explain the math. Sigmoid, sigma, x, equals 11 plus ex backslash sigma, x, equals backslash frac 1 plus e caret x sigma, x, equals 1 plus ex1. ReLU, f, x, equals max, 0x, f, x, equals backslash max, 0, x, f, x, equals max, 0x. Softmax, softmax, zi, equals ezi sigma sj backslash text softmax, z underscore I, equals backslash frac e caret z underscore I backslash sum e caret z underscore j softmax, zi, equals sigma sj z. Explain how these transform features and contribute to decision flow. 7. Semiconductor specific variables. Map AI to domain knowledge. Use PPC terms like shift load, lot size, throughput, tool availability. Show how DNN input nodes consume real-world metrics. Help audience relate formulas to factory KPIs. 8. Output interpretation. Outputs may include estimated process time per unit, yield predictions, recommended equipment assignment. Discuss how these outputs help managers in day-to-day PPC decisions. 9. Use the video strategically. Don't play the video all at once. Use pause points after the input layer to ask what real data they use. After the first hidden layer, review the formula used. At the output, interpret the logic and ask for improvement ideas. 10. Visual analogies. Use analogies like DNN is like a semiconductor fab supervisor working silently in the background. Each layer is like a filter, stripping noise, extracting signal, and forwarding actionable info. 11. Whiteboard sessions. Encourage drawing. Sketch simplified DNN layers. Map input features to decisions. Use formulas visually to trace signal transformation. 12. Engagement tips. Ask open-ended questions. Which process metric would you add to the input layer? What bottleneck this model predict? Use polls or hand votes to keep attention levels high. 13. Feedback loop discussion. Highlight how the AI feedback loop works in continuous learning. Actual vs predicted outputs. Error backpropagation. Weight adjustments. Invite examples where factory teams learn from feedback. 14. Wrap up and takeaways. Summarize key learnings. AI models need engineering insight. Math is the bridge between data and action. DNNs provide interpretability if explained step by step. Share how participants can apply the session in real production discussions. 15. Post-session resource sharing. Provide a printed version of math formulas, screenshot stills from the video, links to reference frameworks, example TensorFlow/Keras for beginners. Offer a WhatsApp/Telegram group for peer discussion post-training. In a deep neural network, DNN, particularly as applied to semiconductor PPC, production planning and control, the hidden layers serve as the thinking brain of the model. They process the inputs using learned weights and mathematical functions to extract patterns and generate insights. Let's break it down in two key parts. 1. Input required by hidden layers, from input layer. Hidden layers don't receive raw real-world data directly. Instead, they receive numerical representations, features, from the input layer, such as direct hit example inputs, from input layer to hidden layer. Input feature description. Wafer quality score, standardized defect rate score. Machine load, %. Load on each critical machine. Shift capacity, number of hours available. Lot size, quantity of wafers in a production batch. Tool availability, binary or percentage of tool uptime. Environmental temperature, degrees Celsius, standardized. Design complexity index, calculated from number of layers or gates. Production deadline constraint, number of hours/days left. These are converted into numeric vectors and passed to the first hidden layer. 2. Output from hidden layers, to next layer or output. Each hidden layer processes the input using neurons, where each neuron multiplies input with weights, adds bias, applies an activation function, ReLU, sigmoid, 10, etc. The result is a transformed output, which represent direct hit processed outputs, from hidden layers. Layer stage output meaning. Hidden layer 1, compressed and denoised feature vector, important variables retained. Hidden layer 2, pattern recognition, example repetitive bottlenecks, defect patterns. Hidden layer 3, probabilistic reasoning, example chance of delay, overutilization. Hidden layer 4, recommendations generated, example line balancing, tool reassignment. Final output layer, actionable decisions, example assign lot number 123 to tool B at shift 2. Repeat button, summary flow diagram. Input layer, hidden layer 1, hidden layer 2, hidden layer n, output layer. Real world features, math transforms abstract patterns, decisions/forecasts. Brain real world example. Input, machine load equals 90%, lot size equals 250, tool availability equals 0.7. Processed in hidden layers. Hidden layer 1 finds feature significance. Hidden layer 2 sees a high risk pattern. Hidden layer 3 suggests alternate scheduling. Mentor point of view, video explanation. Video title, DNN flow. Context, training session, deep neural network, DNN, for semiconductor PPC. Format, animated Sankey diagram simulation. Target audience, small group learners, engineers, planners, AI analysts. Author, Pradeep K. Suri. Welcome to this mentor-led session on deep neural networks for semiconductor PPC. In this training, we'll explore how structured learning can mirror the intelligent flow of a DNN, layer by layer, insight by insight. 1. Welcome and session kickoff. From the mentor's perspective, this video is the opening act of a structured session. It visually introduces the scope of the training using a flow-based animation, rather than static slides, to draw in attention and convey complexity step by step. Magnifying glass tilted left 2. Purpose of visualization. The animated Sankey diagram simulates the logical journey of a training session, broken into digestible units. Inputs, session goals. Hidden transitions, teaching strategies and topic interconnectivity. Outputs, learner outcomes, understanding, engagement, and application. Brain 3. DNN teaching analogy. Each segment in the video corresponds to how DNN itself processes data. Input layer, training objectives, know your audience. Hidden layers, math integration, engagement tips, feedback loops. Output layer, explainable DNNs, tool assignment, post-session impact. This helps the mentor show learners that even the training method mirrors DNN logic, a metacognitive touch. Direct hit 4. Progressive engagement. The mentor uses the animation stages to pause after each step, ask probing questions. How would you define interactive AI? Solicit feedback or peer reflection, activating small group dynamics. Build anticipation using the growing flow, mimicking real DNN weight propagation. Link 5. Topic connectivity and flow. Each animation frame unlocks new links, showing how one domain, example correlate math to AI logic, directly contributes to another, interpret output. The mentor explains how this is similar to a DNN activating forward layers. Error propagation and learning adjustment at each stage. Toolbox 6. Visual teaching tools embedded. The Sankey model allows the mentor to highlight high-priority training segments with color-coded flows. Use real-world analogies like training is like a neural net, you build depth, not just width. Each node here is like a neuron, it triggers the next insight. Repeat button 7. Real-time learning checkpoints. The mentor can use animation stages to create discussion check-ins, example why is peer learning part of know your audience. Run many case activities aligned with the flow. Now let's simulate a bottleneck and see where this applies. Puzzle piece 8. Conceptual integration. By showing math rightward arrow concept rightward arrow application, the mentor bridges theory and practicality. Helps learners understand how formulas like ReLU, sigmoid, softmax convert to insights. Connects DNN principles to real semiconductor PPC decisions. Package 9. Output-oriented closure. The video culminates in the wrap-up node set, where the mentor emphasizes, now you understand the path of training just like a DNN understands a production plan. Reinforces the importance of structure in teaching, just like architecture in modeling. Speech balloon 10. Mentor dialogue style. Throughout the video, the mentor is expected to speak with clarity, using phrases like you'll see here that, or notice how. Switch between explanation, demonstration, and invitation. What would you add to this node? Bring energy while staying technical. It's not a lecture, it's co-discovery. End arrow summary of mentor's role during video. Phase mentor action. Start, set context and goals using visible flow. During animation explain logic, stimulate discussion. Pause points, run questions or whiteboard sketches. End nodes summarize impact, connect to real-world outcomes. Push pin final takeaway. From the mentor's point of view, the video is more than an animation. It is a live instructional framework, a mirror of the DNN itself, where learners experience the same logic DNNs use, but in the context of their own cognitive journey. Explanation of the AI model DNN result. Title, Delay and Priority Chart. Delay expected. Route to tool C. Priority equals high. Author, Pradeep K. Suri. This video visualization, powered by Plotly with a dark theme and animated buttons, serves as a decision support dashboard driven by a DNN, deep neural network, output in a semiconductor production planning and control, PPC, environment. Below is the explanation based on the chart's animated content. Magnifying glass tilted left 1. Objective of the visualization. The main purpose is to highlight tool-wise delays and prioritize scheduling based on real-time DNN inference. It visually guides planners to reroute wafers to the most optimal tool when a bottleneck is detected. Brain 2. Data behind the animation. The dataset includes tools, Tool A, Tool B, Tool C, Tool D. Delay, minutes how long each tool is expected to be blocked. Priority score, models confidence in how critical it is to use a specific tool. The delay data comes from historical and sensor-based input, and the priority score is the DNN model's output calculated using ReLU and softmax layers. Abacus 3. Mathematical processing in DNN. Hidden layers in the DNN process variables such as machine load, tool downtime, lot complexity, wafer volume, shift capacity. Each node uses formulas like ReLU for positive signal amplification, softmax for routing probability, sigma, Wx plus b, for node computations. Clapperboard 4. How the animation works. Frame 1, shows baseline values with tool C already high on priority. Frame 2, DNN adjusts priorities due to shift load, delay on tool C spikes. Frame 3, after mitigation action, tool C is rerouted with reduced load, confirming route to tool C as a good move. Police car light 5. Critical insight from output. Delay expected. Route to tool C priority equals high. This message is generated by the DNN, and it means tool A and tool B are overloaded or suboptimal. Tool C is predicted to be faster and more stable despite a mid-level delay. The priority score, example 9/10, for tool C means it is highly recommended. Direct hit 6. Practical action. Production team uses the dashboard to defer lots assigned to tool B. Assign urgent batch to tool C. Flag tool D for secondary backup. Chart increasing 7. Visual interpretation. Bar chart, blue/orange/red, equals actual delay per tool. Line chart equals AI generated priority score. Animation button lets the viewer simulate different load states. Light bulb 8. Application in Smart Factory. This is a classic example of AI-assisted PPC, where planners respond to real-time alerts. Align lot routing with predictive scores. Minimize downtime, increase yield. Takeaway. This video acts as an AI-based visual alert system, where production decisions are backed by neural intelligence. It simplifies complex back-end calculations into a manager-friendly chart, showing both current state and predictive strategy. Thanks for watching the video.